All right, so some of you having a little trouble on questions 12 through 15, so let's talk a bit about it. It was a little tough, scoured the internet, and found a video actually of what's described in this question. So in this question, a little bit of business about fan cart's background, but when we get down to the meat and potato, they say, turned on, fan cart's given an initial velocity of 2 meters per second to the right. There it is. And they want to see what happens. Now, fan cart rolls forward, slows to a stop, begins moving backward. So what are we actually talking about here? You might need a visual. I think we had one that first day, but actually it's funny how this story's kind of come true. Poor little fan cart's not doing so well. So we found this guy showing us what fan cart actually does. Check him out. Now before he releases, the fan is actually blowing the wind to the right, which means the wind is blowing back on the fan to the left. Basically, if you have the fan behind you, the fan wants to push the car to the left in this video. But young Mr. Ross is going to push the car to the right. Mr. Ross is stronger than the fan, so his push wins. The car is going to go to the right, but the fan is still trying to push it to the left. So you'll see, once he lets go, it's like our problem. The cart now has an initial velocity into the right, but the wind is going to push it back to the left. So watch what happens. You see there, it's slowed down to a stop. If you watch a blinking light, you would get something along the lines of blink, and it ended here. It was going fast in the beginning, and then it slowed down, and it slowed down, and it slowed down. Something like this. That's a blinking light pattern you just saw as the fan cart moved off to the right. But now it comes to a stop, and the fan is still blowing. So it now starts to accelerate back to the left. Let's see. There it goes. And in fact, it follows the same exact pattern going back to the left. Let's see here. Maybe something like here, and here, and here, here, here. It's going the fastest when it returns to young Mr. Ross's hand. Okay. So this is showing you the acceleration is actually the same, both in magnitude and direction. As it's moving to the right, the acceleration is, notice the big spaces, to the left. As it's moving to the left, the acceleration is to the left, and they line up with each other. And there's a reason for this. And this is beyond what we're learning right now, but I'll give it to you anyway. Acceleration. There we go. Let's shrink this down a little. Is caused by force. So, same force equals same acceleration. What do we mean by that? In this case, the force is from the air, fan. So basically, we have same fan blowing the entire time, at the same speed. I'm not going to write that, it would be confusing, but the blades are spinning with the same speed. So same fan blowing the entire time. Also, it's blowing the same way. It's blowing to the right. So same fan blowing the entire time, same acceleration the entire time. Okay? It kind of gives a backdrop of what's happening up here. And Mr. Ross will give us one more because it was pretty cool. I'm with you, Mr. Ross. Watch it now. The fan slows it down and then speeds it back up. So while the velocity changed direction, the acceleration did not. The acceleration followed the exact same pattern that we saw in the green and the purple dots, the magenta, or whatever those are there. Okay, so let's get on to some business here. Let's get to some of these questions. Now we'll look at 12. So a fan cart rolls forward, slows to a stop, begins moving backward across the starting line 5 seconds later. What is her average velocity? Well, this one's pretty straightforward. If you look at 12, check out the givens. Just to be quick, I'm not going to write that. Yes, I will. Givens with you, bitch. All right, here we go. So we know the VI was 2 meters per second to the right. Let's call right positive. Let me put a little comment up here. R equals, that's not an R, equals positive. Shrink this down a bit. Okay? And what else do we know? Just from this one, the time is 5 seconds. And you know that it crossed the starting line. That tells you something. It's back to the start, which means the displacement is 0. And of course, they ask for the average velocity. Now, here, this vector business really matters. So let me draw them in right quick. There we go. Bring this sucker out. So this is definitively a displacement that's 0, not a distance, an initial velocity that's 2 meters per second in the positive direction, and an average velocity. So here we have the V bar. It's a little hard to tell. You might even write VEL down here so you know it's velocity. Actually, some textbooks, the way they get around that is they make the letter bold. They actually would do something like this. You let me write in there? Yes, you will. Something like this. You see how it's bold compared to the others, then you know it's a vector. So some books do that. Well, this is pretty straightforward. Here, equation. Now, just be sensible. You better know your definition. The average velocity, I'll do it bold this time. The average velocity equals displacement. That's a displacement, not a distance, over, the spacing's a little funny here, over time. And so knowing the displacement from 12, boom, you got this knocked out. All right, cool. Let's go over the next one over her. Let's look at 13. Okay. Some people have a little trouble with 13. Well, now that you've seen this video, it might actually make it a little easier for you. I'm going to get them given with unit again. Let's get all this junk right over here. All right, so your VI is still 2 meters per second. Now, knowing that the displacement is 0 at the end, knowing the average velocity is 0, you could run some math with this. You might just realize this. Notice I didn't ask you for 2-point format on this. I didn't ask you for 2-point format or show all work, etc. on number 12 either. In fact, these are questions that right here you can kind of just know. But anyway, we can do this one with an equation. However, let me tell you quickly. Can you know it? Sure you can. If it started out going to the right, and it came back to the same starting place and has the same force, it's going to slow down to 0 and it's going to speed back up to the exact same velocity it was going before. Same speed, rather, as going before, but the velocity is opposed in the opposite direction. So you can know right away that the VF is -2, and that can give you the change in velocity. But let's assume you didn't know that. Let's say you only know the VI. You know the V bar, I'm going to put it bold for velocity, is 0 meters per second. You want to know the delta V. I'm going to put a triangle in there, space, question mark meters per second. So I'll draw a little delta in there. It'll be a lot of fun copying this over 4 times. You let me draw it? I know you're telling me get on with it. It's 10 o'clock at night. I don't need to see it that perfectly. Well, let's do it just in case. Get it looking right. Okay, so delta V. What's your equation for delta V? Better know it. Better know it. Delta V over here. Oh no, don't do that. Okay. Delta V. I'm going to make it bold because we know it's the vector version. Change in velocity, of course, equals VF minus VI. So you may just realize this one, but I'm telling it to you because you better know it. Okay, so here, notice you need VF. Let me see here, and we're looking for, good, VF minus VI. That's one way to get delta V. Another one is A times T, but you don't know the acceleration. So here we're still sitting like, okay, this is cool, but we don't know our VF. How are we going to get our VF? Well, can we get our VF from the givens over here? Well, actually, as it turns out, we can. We can do a little secondary equation. Remember those. How are we going to do that? Well, we got V bar. V bar equals VI plus VF, whole thing, one more, over 2. And we're doing this. So in truth, it is certainly easier just to know this than it is to go through the math I'm giving you right here. But if you need math, you need formality with it. There it is. And so you can solve this now. This is V bar. Let me draw that in there so you don't have any confusion about that. This is V bar. Oh, that's a big clunky bar. This is V bar over here. And we got to solve for V bar over here. So, sorry, we know V bar. We got to solve for VF over here. That's not such a hard thing to do. Of course, you can run your numbers, but 2 times V bar is going to be, V bar is 0. So you may say, wait a minute, I'm going to run the numbers for you. I'm going to run them for you because you probably feel like this seems foolish. How could this be? But you'll see, it works. Trust the numbers. Go with it. 0. Here we go. Equals VI, we know is positive 2. Plus VF, we don't know. All this thing over 2. So do it. It's easy. Cross multiply. 2 times 0 is 0. So what are you left with? 0 equals 2 plus VF. Subtract 2 from both sides. What's VF? Boom. There it is. Seemed tricky, right? It wasn't. VF equals negative 2 meters per second. There it is. Now we got what we need. So now delta V, we plug this in. Don't get lazy. Delta V equals negative 2 minus positive 2, which equals negative 2 minus 2, negative 4 meters per second. And since we called right positive, we might call this 4 meters per second to the left. There it is. So you can just know this problem. You can just know this by recognizing there's a symmetry. It starts out fast, it slows, starts out at 2, it slows down to 0, it speeds back up to 2, except in the other direction. So this one's a little tricky, just beware, because they're in opposite directions, that actually does equal something, not nothing. So negative 2 minus 2 is negative 4. Even if you switch the directions around, you would have had 2 minus negative 2, which would have been 2 plus positive 2, which would have been 4 also. Okay, let's look at 14. I know that was giving some headaches. Okay, let's look at 14. We're still calling right positive. 14, excited by her accomplishment. Fan cart keeps on riding for another 5. So if you didn't get 13, you're going to have a little trouble with 14. But the cool thing about this one now is, so if we look up here, our initial condition was really a velocity this way of 2 meters per second. There's an acceleration. The acceleration, so this is V. There's an acceleration the whole time going the other way. So the acceleration is this way. We don't know what it is yet. On the way back, the acceleration is also this way. And when it returns to this same position over here, the velocity now is this way, 2 meters per second. All right, and so whether this is your initial, your final, whatever, that depends on when you want to start the problem. So this one, by the way, was what we call T0. This one was at T 5 seconds over here. And of course, probably not surprising, although we didn't need to know it, this point over here happens at T 2.5. It's going to happen at the mid-time. Notice it's very symmetric. When you have this constant acceleration, when something is slowing down and then speeds back up, you get all these symmetries that come out. We're going to use that a lot in the next unit, in Unit 3, when it comes to throwing things up in the air. Okay, so let's keep going over here. Handcart keeps on riding for another 5 seconds. Fortunately, having visions, Lumpy is there with the quick hands. Good for you, Lumpy. You catch Fancart. What was the Fancart's velocity at the moment of the catch? But what you have to realize here is that we have a new starting point. This is now our starting point. Before, this was our ending point. This was our final condition for the original problem. This was our initial condition for the original problem. And now we have a new set. This is our new initial condition. And the final condition is going to happen somewhere over here. Fan cart is going to continue to speed up in this direction. And so we had a dot. So not here, maybe like here and here. Of course, that timing is off. We'd have to go off the page to get a full 5 seconds on this drawing. Let's put it right around there. So this is farther along, whatever. Let's say here is going to be our new final. So this is our new initial condition. And this is going to be our new final condition over here. And now this is another 5 seconds. So with our new initial condition, this now becomes T0. This now becomes T5. The neat thing is the velocity that we had here of 2, it's still 2, except that's now our VI. And so what's going on here? What's fan cart's VF over here? That's what we're looking for. So let's run some numbers, numero, new something, I don't know. Okay, let's go over here. So you got VI equals 2. Yeah. Meters per second. We got VF equals question mark meters per second. We got time equals 5 seconds. Now what? Oh, this is a tricky one, isn't it? Sure it is. We need to figure this out. So let's pick an equation. And that's the key here. This, by the way, this is by no means intended to be an easy layup problem. You've got to set something up here. There are a lot of different VF equations. I'd like to go with the easiest one because if that works, cool. VF equals VI plus AT, that would be nice. Do we know fan cart's acceleration? I don't know. You might have to go figure it out. A little secondary equation here. Could we get fan cart's acceleration? Well, maybe we could. In fact, what would help us here is to realize that the acceleration is the same throughout the entire problem in the green dots and the magenta dots the whole time. So do we have any other givens that maybe would help us? Yeah, actually we do. And by the way, there is more than one way to skin this cat too. I'm noticing something I was a little sloppy over here. If we want to call right positive, which we don't have to, we want to call right positive, then the VI that we're looking at right here would actually be negative 2 meters per second. VF is our question mark. Of course, you could switch it to left as positive here if you wanted to. So how could we possibly get acceleration? And again, it's not an easy question for you. You really have to dig deep. Well, maybe we can get it from like the earlier part of the question. And as it turns out, you can. From earlier in the question, you could say VI was positive 2 meters per second. Going to give us some luck? Not on the spotlight search. Let's go. 2 meters per second. We knew actually a VF from earlier was negative 2 meters per second. And we knew the time from earlier was 5 seconds. So we could definitely get the acceleration from earlier, and that's going to be the same acceleration as now. And that's just VF equals VI plus AT again, except we're using it with a different set of givens because it is using the same acceleration it had before. It's the same fan, the same cause. So acceleration equals, let's see, VF, if you rearrange it, VF minus VI over the time. So VF negative 2 minus VI minus positive 2 over 5 seconds. There we go. So the acceleration comes out to, that's negative 4 over 5, or negative 0.80 meters per second squared. Not surprised it's negative. We said it went to the left. So now we can take that acceleration and pop it in over here. Oop, there we go. And we'll get our answer. So VF equals -2 plus negative 0.80 times another 5 seconds. And of course, I don't like this stringed out equation. You should write it in the next line below, but type it out here. It's a little slow. It's going to be -2 minus 4, which is going to equal -6 meters per second. All right, cool. There it is. There it is. You could have done this actually with the original initial velocity as well. You could have done this separately. I'll write it down over here. You could have done this with VI. VI equals +2. But what would the time have been? The time would have been, in that case, the 5 seconds to go 2.5 to here, 2.5 to here, and then another 5. Time actually would have been 10 seconds from that point. And this would still work out, by the way. VF is what you're looking for. You would still have to have gotten that acceleration, which came out to -0.80. And, just for fun, so you see it, VF equals, this case is +2 plus -0.8 times 10, which is +2 minus 8, which would still be -6. So, by the way, that -6 is, of course, just 6 meters per second to the left. So no matter how you skin this cat, it works. Okay? And then 15, in which direction did fan cart accelerate throughout the ride? Same the whole time, of course, left the entire ride. Okay, net effect of this. I can't kill you too much with this tomorrow because we, in reality, have not really done much with fan cart in class because actually she's been broken. So you may get a little something like this where a thing goes forward and backward. We did something going up a hill and back down. But you're not going to get beat up with 4 questions on this sort of thing. So this is more of a, probably we'll do a little more on not the next, but 2 quizzes down. This is going to transition us a bit into the vertical problems. So don't lose your mind, but there it is. There's those challenging fan cart problems. Okay.